When the first reports appeared of nanorod motors swimming toward higher concentrations of hydrogen peroxide, the headlines made it sound like chemistry had just reinvented life. Tiny machines that sniff fuel and chase after it like bacteria hunting food. The term chemotaxis, long reserved for living organisms, was suddenly applied to platinum-gold nanorods only a few hundred nanometers long. Was this really a glimpse of lifelike behavior in a machine, or just physics in disguise? At its core, the phenomenon is elegant but not mystical. Platinum catalyzes the decomposition of H2O2 into water and oxygen. If one end of the rod has platinum and the other does not, the asymmetric reaction generates self-phoretic flows. The result is propulsion. Now, when a concentration gradient of peroxide exists, the local reaction rate differs along the rod's trajectory. Slightly faster where fuel is richer, slightly slower where it is poorer. Over many steps, this bias nudges the rod into swimming up the gradient. From a physical chemistry standpoint, nothing exotic is hiding here, just surface catalysis, diffusion, and gradients. So why was it treated as a breakthrough? Because it shifted nanomotors from mere toys that move into systems that sense and respond. For the first time, synthetic particles were not just drifting randomly or being steered externally, but exhibiting autonomous taxis, a directed preference encoded in their interaction with the environment. Isn't it uncanny that something so simple, fuel plus asymmetry, could mimic such a hallmark of biology? Skeptics were quick to point out possible artifacts. Gradients in peroxide can also generate flows in the bulk liquid, Marangoni effects, bubble currents, or even subtle convection from heating. What looks like motor intelligence may sometimes be fluid dynamics dragging the particle. Careful controls, passivated rods, inverted gradients, and microfluidic setups eliminating flows are essential to prove the effect is truly chemotaxis and not a glitch of the experimental geometry. This debate still simmers. How much of early data was genuine chemotaxis, and how much was unrecognized hydrodynamics? But even if the underlying mechanism is just physics, the importance remains. Biology itself is just physics and chemistry, yet chemotaxis in cells is celebrated as life's defining trick, turning noisy gradients into purposeful action. The nanorod experiments remind us that lifelike behaviors emerge naturally from non-living matter, given the right asymmetries and gradients. Whether we call it breakthrough or refined artifact, it signals a new scientific frontier, using far-from-equilibrium phenomena to design particles that adapt to their surroundings. Perhaps the haunting question is this: if chemotaxis can arise so simply in non-biological rods, then where exactly lies the boundary between physics and life? Are such experiments mere curiosities, or are they showing us the first primitive steps toward chemical computing and synthetic lifelike systems? In that sense, even a glitch can be profound. The first reports of catalytic nanorods moving up hydrogen peroxide gradients were presented as evidence of abiotic chemotaxis. The idea was that motors not only self-propelled, but also actively steered toward higher fuel concentration. This appeared analogous to bacterial chemotaxis, but achieved without receptors or signaling networks. The significance was framed as synthetic matter mimicking lifelike navigation. Such experiments hinted at the possibility of designing smart nanomachines that sense and respond to their environment. The scientific community saw potential links to artificial cells and nanorobotics. Platinum-gold nanorods were observed swimming preferentially toward peroxide-rich regions. It was like watching a toy boat steer itself into stronger currents without a rudder. Skeptics argued that these results might not be new biology-like behavior, but consequences of standard physical laws. Diffusiophoresis and self-generated gradients around motors can bias their direction of motion. Particles in asymmetric concentration fields naturally drift due to local osmotic pressure differences. In such a view, the motion is not sensing, but passive alignment with chemical flux. This means chemotaxis is just a redistribution effect from gradients, not intelligent navigation. The debate is whether this constitutes novelty or a trivial outcome of continuum transport theory. Colloidal particles drift in salt concentration gradients even without motors or fuel. It is like smoke drifting toward open windows, not because it chooses, but because air pressure pulls it there. To test true chemotaxis, strict experimental controls are needed. Dead motors, symmetric gradients, and passive tracers should be included as references. Without these, background flows or slight asymmetries can produce false positives. Moreover, small temperature gradients from peroxide decomposition could mimic directional bias. Controls must rule out all classical artifacts before claiming a breakthrough. Otherwise, the effect risks being labeled a scientific glitch. In some studies, passive gold beads showed the same drift as active nanorods. It is like mistaking a leaf blowing in the wind for a bird actively flying. If nanorod chemotaxis is real, it must be understood in terms of energy transduction. Motors consume chemical-free energy from peroxide decomposition, producing gradients in turn. Their directed motion reflects entropy production and bias beyond pure diffusion. The challenge is quantifying how much information about the gradient is extracted per unit of energy dissipated. If this bias can be captured by stochastic thermodynamics, it becomes a genuine information engine. Without such accounting, the claim remains qualitative. Tracking motor trajectories shows a measurable alignment between velocity vectors and gradient direction. It is like auditing a company's profits. You need the books to prove there's more than random fluctuation. At the microscale, Brownian motion competes with propulsion, making chemotaxis detection noisy. Substrate interactions and wall effects can also bias trajectories. Fuel decomposition often creates local microflows that complicate analysis. As a result, distinguishing active chemotaxis from passive drift is extremely difficult. This is why interpretations remain contested decades after first reports. Only precision microfluidics can separate signal from noise. Motors placed in carefully designed microfluidic gradients show weaker but more reproducible biases than in bulk. It is like trying to hear a faint melody in a noisy crowd. You need headphones to tell if the music is real. Even if chemotaxis in nanorods is just physics, it is still scientifically valuable. It shows how chemical energy, diffusion, and geometry interplay to bias motion at the nanoscale. These mechanisms are the very foundations of self-organization in active matter. Moreover, they provide testbeds to refine theories of stochastic transport. Engineers can harness such effects for applications whether or not they resemble life. Thus, controversy does not erase relevance. Nanorod chemotaxis has been proposed as a mechanism for environmental sensing in microfluidic chips. It is like arguing whether kites fly or just ride the wind. The function still matters. If chemotaxis is reproducible, swarms of nanomaterials could be programmed to explore gradients. Their biased trajectories would act as distributed sensors, encoding environmental information. This could form the basis of chemical computing, where motion itself processes data. Swarm-level navigation may enable map reconstruction without electronics. Such systems promise energy-efficient computation directly in fluids. The leap from curiosity to technology depends on reliability. Motor swarms could collectively map pollutant gradients in water sources. It is like using a flock of birds' paths to trace the shape of the wind. The key question is whether chemotaxis of nanorods adds fundamentally new knowledge. If results are artifacts of flows or gradients, the breakthrough dissolves into known physics. If instead the effect survives rigorous tests, it marks the first abiotic analog of a biological navigation strategy. Either way, it stimulates methodological progress in active matter research. What matters is not the label, but the reproducible physics uncovered. In science, even a glitch can reveal hidden dynamics worth studying. Follow-up experiments with stricter controls found weaker but still significant gradient-following behavior. It is like a magician's trick. Once explained, either you find only illusion or you discover real mechanics behind the spectacle. The paradox is that what looks like life, like sensing, might be reducible to basic physics, yet this does not trivialize the phenomenon. Physics itself explains how abiotic matter imitates biology. If validated, nanorod chemotaxis blurs the boundary between living and non-living systems. If refuted, the search for abiotic intelligence in motion continues with stricter standards. Either outcome deepens understanding of how matter organizes in gradients. Thus, the nanorod chemotaxis story is less about yes/no than about refining the language of discovery. Surface nanobubbles and catalytic nanorods both exhibit puzzling stability and bias unexplained by simple models. It is like a mirage in the desert, whether illusion or real oasis. It forces travelers to question what they see.